Before starting this video, I want to let you guys know that Coding Cleverly also has a Patreon page. So go to patreon.com/codingcleverly and you'll see that there is a Patreon page that is available, and you guys could support the channel by just joining any one of these tiers. You guys also could become my patrons. That would also motivate me to provide better and better content. So all you got to do is go to this page and show some love to Coding Cleverly. Enough with the shameless plug. Now let's go to the video. It's coding time with Coding Cleverly. Today we're going to be writing the binary search tree algorithm. We're going to have the binary search tree.java file created. So it's in a directory here, and I just have the binary search tree. And I also have it in just public class binary search tree written over here for me. So in the previous video, we watched and learned how to create trees, and they're pretty easy. And today we're going to be making binary search trees. It's just a modification, an investment, just kind of modified version of a tree. So a binary search tree is an efficient value structure for fast O of log of n data storage and retrieval. It is a specialized tree data structure that is made up of a root node and at most 2 child branches or subtrees. So we have something at the root, and we have at most 2 child branches or subtrees. So you could see over here 2 child branches or subtrees. We could consider these as subtrees as well. So this is a tree and this is a tree. I call them as subtrees, and the main tree is the whole thing. So in our implementation, each node will be an instance of the binary search tree class. So all of these nodes you could see over here, these green balls, you're going to see all of these as instances of the binary search tree class. Each binary search tree node will have the following properties. It will have a value. You can see it 28 is over here. A depth value, where a depth of 1 indicates the top level of the tree, and a depth greater than 1 is a level somewhere lower in the tree. So by default, the first level is 1. It's the root level. And then if you go down, it's going +1, right? So it will have a value. So you can see over here 28. It will have a depth value, and in this case it's 1, and then it's 2. Now we have 2 things. Now the third thing is that we should have a left pointer, and the fourth thing is a right pointer. So a left pointer that points to a left child, which is itself a binary search tree and must have a data lesser than its parent node's data. So over here we have 17 and it's lesser than 28. So we're doing great over here. And the right pointer that points to a right child, which is itself a binary search tree and must have a data greater than or equal to its parent node's data. So in this case, we have 32 and it's greater than 28. And in this case, you could also have something equal. So you could have 28 and 28 over here, and it's completely valid. With all of that out of the way, we're gonna now construct the binary search tree algorithm. So the first thing it was, I said public, I needed a value for this. I also needed some depth for this, so a depth value. I also needed a pointer, so I added a pointer for the left and the right subtree. But I could use the instance of binary search tree over here because they're both going to be binary search trees, and I could say this as left, and Alt Shift and down, this would be as right. Once we're done with this, now we could create our constructor here. So I would say public binary search tree. So in this I would put in a value, and I would also put in a depth value. Here I would say the instance variable, which was value, is assigned to the parameter value, and the instance variable depth is equal to the parameter value depth. After this, we could create another constructor, and in this case, we'd have the value passed in. Now I'll tell you why we have to do this. So the instance variable value would be the same. It would just equal to the parameter value, but the instance variable depth will equal to 1 by default. And this dot left would equal to null, and this dot right will also equal to null. Just null pointers here. So we could copy these 2 references and paste them here as well, because we might need them here. Now let's create the insert method. To go about this, first we're gonna write the code, and then after that I'm gonna explain it in detail. Public void insert int value. Inserting is pretty simple. We wanna insert something in our binary tree, right? and we're passing in a value that we want to add. So my binary tree has integer data. That's why I'm passing in integer value. First of all, I have to check if the value that I passed in, so this is my target value, the input parameter, if that is the less than the this dot, let's say we are in our binary search tree and we want to add 59 inside, right? Now, according to our binary tree, we have some kind of rules that we set. We have that the left one will always be lesser than the root node, and the right one, the right subtree value, will always be equal or greater than the value of the root node. So in this case, it's 59 and it's greater than the root node value, which is 43. That means it will go to the right side. It will check if it exists or not. If it exists already, we're gonna have to call the insert method here. So we're doing some kind of recursive algorithm here. And then we're gonna check, okay, so 59 is greater than 52. So we're gonna check first the value over here. If it's greater, then we're gonna move here. If it's lesser, we're gonna have to move over there. In this case, it was greater, so we have to move here. And now it's going to 65. So we check over here if 59 is greater than 65 or less than 65, and in this case 59 is less than 65, so we're gonna add this new one here. So 59 will be placed here. So this is our insert method, and we have to adopt something like this. We got to create something, and that's why I said over here public void insert the value that we did, 59, if the value, so if its value is less than this dot value, we'll go on the left side and perform a recursive insert, and if it's greater than that, we'll go on the right side and perform a recursive insert. If this dot left, if that is equals to null, so if it's equal to null, that means it doesn't exist, right? So we could just place it using the following code. We could say this dot left is equal to a new binary search tree instance, and we paste in that value over there what we passed in. Awesome. So we created something like that, but we also need to add in the depth over here as well, because this, in case if it doesn't exist, in some cases it would be in somewhere on the bottom. So the depth would change, not 1, but it could also go to 2, 3, 4, 5, and so on. So we have to say this dot depth. We got to modify the depth by +1. So it was the first constructor that we created over here with the value and depth. So in this case, if you wanted to pass something like 29 and nothing was existing here, there's nothing. So you check the left side and there's nothing over here. So you could easily put 29 here. That's it, nothing else. But in the other case, if it was gonna cause some problems, then we're gonna have to provide this else condition here. So if it already existed, what do we have to do? This dot left side, and we're gonna call it using the left side. So this dot left dot insert here, and we're gonna call the insert with the same value, target value that we passed in as our input parameter. Awesome. In the other cases, that if the value is greater than the root node's value or equal to the root node's value, not less than, but we're going to go to the right side. And in this case, we're going to check if it exists. If it exists, perfect, just place it in. But if it doesn't exist, like in this case, we're going to have to do some kind of recursive insert and just find our way to find some empty space so we could add our newly added thing. So over here, we could say else doesn't exist. So in case if it doesn't exist, right, in like just case in our first one, so what we say is this dot right, and we assign it with new binary search tree and pass in the value also with the depth. So we could just add in the depth with our value as well. Say depth +1. So we are done with that. And in case if it does, if there is something already in the right side, we're gonna have to use a recursive method here. So we're going to use the similar case, this dot right, and we're going to apply the recursive thing. So the thing is insert. We're going to use that method inside of the right subtree, and we're going to pass in that target value, same one, and that's it. So this will help us add in our value, and there you go. So this is our entire insert method. We're going to the next one. Now that we have successfully added our insert method, now we're going to create a method that would get a node by its value. So we're going to say public binary search tree, and we're going to say get node by value, and over here we're going to pass in int value, and over here we're going to just get the body started here. We have a binary search tree method which is called getNodeByValue. It's self-explanatory. It's going to get the node by its value, and this is the value that we have to pass it in. It's going to return us a binary search tree object. So here we have a couple of conditions we have to consider first. I want to get the 28. By default, we're going to start with the root all the time. So the root is on the top. And the first case is that if the value is the root value. So if the target value is equal to the root value, I'm just going to return this thing. That's it. So this is our object, the binary search tree object. But in other cases, if it's not equal, so it's not equal at it because 28 is not equal to 43. So we're going to have to move either 28 left side or right side. That depends on the value, what I gave to the input parameter. Let's write this baby up. So we're going to have if, and we're going to see this dot value. And this is the value, for instance, this is our targeted value, but this is the value that was our root node. So if that root node value is equal to our targeted value, then our job is done here. So we just have to return this, and that's it. We got our root node. So if I say our value, which is targeted value, was less than this dot value, so we'd have to go to the left side, right? And we also apply an AND operation here. So I'm gonna find the ampersands, and we also check if this dot left not equal to null. If the targeted value, which was in the input parameter, is less than the root node's value, then we go to the left. And if the left pointer is somehow, there's something inside of that left pointer, right? So that if there's something existing, we're going to do a recursive call. And we're going to do the return recursive call. So we're going to say something like return, and we're going to say this dot left dot get node by value, and we're going to pass in the value, and there you go. That's enough. If the value and this is the targeted value is greater than the root node's value, right? And this could be any, it's going to be not only the root nodes, but it's also going to be the current nodes, whatever it's going to be there. Targeted value is greater than our current node's value, and we also say that the left portion, and now we have to say the right portion, and we have to say right also has some items here. So we say this dot right, and we're going to recursive call getNodeByValue, and we're going to pass in the value here. And then after that, we just have to put a safe return here at the end if nothing happens. So in our case here, we just return null if somehow we don't have any results. So this is just gonna keep going recursively until we find our value. And once we find our value, we return that instance of that value. And that should be returned here. And if we don't find anything, so that would just return null, indicating that that kind of value doesn't exist in our binary search tree. What is traversing a binary search tree all about? There are two main ways of traversing a binary tree: breadth first and depth first. With breadth first traversal, we begin traversing at the top of the tree's root node here, displaying its value and continuing the process with the left child node and the right child node. It's just going root node, and then we go one step down, left to right, then one step down, left to right. So this is how we're gonna implement our breadth first traversal. But in case of depth first traversal, with depth first traversal, we always traverse down each left side branch of a tree fully before proceeding down the right branch. However, there are three traversal options. We got pre-order, in-order, and post-order. Pre-order is when we perform an action on the current node first, followed by its left child node, and then its right child node. So we perform on the current node first, then its left child node, then its right child node. That's pre-order traversal. Then we have in-order traversal, in which we perform an action on the left child node first, followed by the current node and the right child node. So we have left child first, followed by the current node, and then the right child. This is our in-order traversal. And then the last one is post-order traversal, is when we perform an action on the left child node first, followed by the right child node, and then the current node. So left child node first, then the right child node, and then finally we put on the current node. So that is our post-order traversal. And in this video, I'm going to be implementing the second option, the in-order option. Like I told you, in-order is when we perform an action on the left child node first. So this will be implemented. We follow the current node, which is this one, and then after that we follow the right one. So that's the in order. And what's the benefit here? There should be a benefit, and there is. So the advantage of this option is that the value is displayed in sorted order from the smallest to the biggest. So let's go here and create our depth first traversal. Depth first traversal. We just gotta first provide a condition here, and we have to check if the left pointer not equal to null. So if there exists something in the left side, right, we're gonna go to the left side like that. So we're gonna do a recursive call, and we say this dot left dot, and we say depthFirstTraversal on the left side. And there you go. It's just gonna keep going at the end till we find the bottom pit here. And then after that, what we do is we console out the value here. We say system.out.println. We're gonna say the current value will be printed out here. So it's gonna be this dot value. We also have to check the right portion here. We have to say this dot right, and we say not equal to null. And then we're gonna do the same thing. We're gonna recursively go using the right pointer as well. So we're gonna say depthFirstTraversal here as well. And that's it. This is our depthFirstTraversal algorithm. Wow. And we use the Inorder method. So that was pretty sweet. So in our main method here, we have a string that's printed out, creating binary search tree rooted by value 20. This is gonna be our root value. After that, we have a tree instance, a binary search tree, and this is gonna be our root node. So new binary search tree, the value would be 20. It would have a depth. It would have the left and right. They will be set to null for now. And then after that, we're gonna insert stuff. So we could either do this tree.insert, insert our values individually, and we'd say 33, and just add in some more. So let's say, I don't know, 50. Let's say 63 and 343, and this will be implemented. After that, we could just print it out using the methods that we created. So because we don't have any print statements, we're not going to know what's going on here. So we just have to add some print statements in our insert method. So we just put a fancy print statement here that says tree node %d added to the %s, so %d add %, whatever these percentages. I'll tell you these percentages are integers. The %s is a string. So tree node %d meaning the targeted value, the new one, added to the %s left side to the %d, which is the current node, whatever this dot value was, at depth, and then the value of depth, which was this dot depth plus 1. And there you go. So we created for the right. Just gonna change this to right. And now once we're done with this, let's go down and we'll see what's popping here. So let's go. So it's binary search tree. I'm gonna say binary search tree.java, and then we say Java, and we say binary search tree.class, and there you go. Once we created our binary search tree, you have creating binary search tree rooted at value 20. Tree of node 33 added to the right of 20 at depth 2. Why? Because right now it's the depth is 1, the value is 20. That's the root node. Then after that, when we want to picture this, so if you guys are really interested to see how this works, go grab a notebook and try to map this out. So whatever I created right now, 33, 50, 63, and 343, but we have 20 here, so that's the root node. Tree node 33 added to the right of 20 at depth 2. So this is 2, definitely, then 3, then 4, then 5. This is working correct. And it says tree node 33, because the 33 was what? Greater than 20, that's why it's added to the right of 20. Perfect. 50, which was this one, is starting with 20, so it's greater than, so it's gonna go down to 33, and then after that, it's in depth 2, it's gonna go to depth 3. So added to the right of 33, amazing. And then after that, 63 added to the right of 50, because it's greater than 50, and it's going to go to the right. Awesome. And this is going to right, and just going to right all the way. So this is I just created an imbalanced tree. If you drew that picture on your notebook, it's an imbalance because it's just screwed to one direction. After this, I'm going to remove this insert method. So I created a for loop that goes from 0 to all the way to 9, and this is going to create some 10 different instances of our binary search tree class. And I'm using the math.random function multiplied by 100, which gives us 0 to 99 of different random numbers. So it's going to be in the range of this, and then we're going to insert them one by one in our tree. So it's going to be 10 different numbers in the range of 0 to 99. Not sure about that. Should write your comments in the comment to let me know. And then after that, we have system.out.println, and we're having printing the Inorder depthFirstTraversal, and we use the depthFirstTraversal also for this case. So let me just add in a \n here as well. So I'm just gonna, so now let's run the final version here, and let's go here, binary search tree, compile, and then after that run. So we created 10 different instances, and this should be 10. And then after that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see the range is also correct. It's in between 0 to 99. Printing the Inorder depthFirstTraversal, and you can see that it's sorted in depth traversal. It works correctly, and the Inorder depthFirstTraversal is also correct by the fact that it's an ascending order. So 8, 9, 15, 18, 20, 22, 25, 37, 72, 86, and 86. Perfect. That was amazing. That was so cool. I enjoyed making this video. I hope you got so much benefit out of this. Please give a subscribe to the channel, like this video, share it to everyone. Support Coding Cleverly by being a Patreon on the Patreon page. Thank you so much. See you in the next one. Peace out.